Welcome back to the third part of Lesson 1, Unit 2, the derivative of a function. So far we have learned how to find the derivative of a function by using the first principles formula and discussed the intervals of increase and decrease using the first derivative sign. And we've also learned how to graph the derivative of a function using the graph of the function itself. So we're now moving on to a different type of exercise where we're given some information about some of the points on the graph of a function and the values of the derivatives at those points, and we will have to shape the graph of the derivative. So let's get started with the example B3. We have to sketch the graph of a function that satisfies the following conditions. So we're told that f of 1 equals 3. That means that at x equals 1, y would equal 3. And f prime at 1 is equal to 1. That means that the slope of the tangent drawn at x equals 1 would be equal to 1. So what I'm going to do is I'm going to plot this information on the grid. So x equals 1, y equals 3 will be a point somewhere here. And I will draw a straight line with a slope of 1 here. So I'm going to draw a straight line. I don't want to make the line too short, too long, I meant, because I have to draw the graph of the function and I want the graph of the function later to stand out here. The next piece of information that we are given here is that at x equals 4, the value of y is 5. So that means the point with coordinates 4 and 5 is a point on the graph of the function. And we also know that the value of the derivative at 4 is negative 2, which tells me that the slope of the tangent to the graph drawn at x equals 4 would equal negative 2. So first I'm going to plot the point with coordinates 4 and 5. So here is 4, 1, 2, 3, 4, 5. So this is 5. And the slope of the tangent here is negative 2, which means that we're going this way. So, and I'm going to draw the tangent around here. Okay, and I know so far from the information given that this graph will have to pass through these 2 points, and it must follow the tangent. Now remember that any graph, and I'm going to draw an ordinary curve in here, the graph will be nested in the tangents, right? So it can be below the tangents or it can be above the tangents. Okay, and that's something we'll discuss more in the future lessons. So it seems that the tangents in here are going one in the positive and one in the negative direction. And the positive comes first, the negative comes after. So it seems more like this scenario, right? Rather than this, right? Which means that the graph is probably going upside down. So I'm going to sketch some graph in here, and I'm going to try to make the tangents even shorter to allow me for a better prediction of the shape of the graph. And here we go. I'm going to try my best in here to draw a graph. So I would say that the graph of this function would be similar or something like this one here. Okay, so moving on to the next example, here we have more information given for the graph of this function. We know that f at negative 3 is 5, and f prime at negative 3 is negative 2. So what I'm going to do is locate this point first and draw the tangent of negative 2 at that point with the slope negative 2. So here we go. X negative 3 means that we are in 1, 2, 3. Y is 5, 2, 3, 4, 5. So it's right here. So this is a point on the graph of a function, and the slope of the tangent here would be -2. So I'm going to draw a line, a straight line with a slope of -2 here. Okay, now the next one, the next point given is f of 1, and at 1 the y value is 2, the derivative is 0. So at x equals 1, y is 2. The derivative is 0, which means that the tangent will be a horizontal line. And the last piece of information given here is that at 4, the y value will be -2, and the derivative will be -3. So x equals 4, so 0, 1, 2, 3, 4. Y is -2, so -2. So that's where the point is located. And right here we have a slope of -3. So that means that I have to draw a line in here, a straight line with slope of -3. So down 3 and to the right 1. So now we're thinking of where the function would be. Now remember that the slopes here are leading us towards this direction. So it makes no sense for the graph to go like this, right? Because then it will have to make some other, curvy shapes down here. So it makes more sense for us to see the graph going this way, and then this way around. And I'm going to sketch this one, okay, this graph. So let me try, and hopefully I'm going to get a nice shape here. Okay. And so hard because the pen is very slippery on the screen. So here we go. And I'm going to make this slightly more pronounced here. Pay attention. Okay, so this would be the shape of the function, and we are drawing, remember, all these functions, all the graphs. We are sketching them. They're not very precise, but the point that we were trying to make is how, knowing the derivative of a function, we can shape the graph of a function. So we're going from derivatives to the graph of the function. And like in the previous examples, when we had the graph of a function, right? And then we drew the derivatives after. So is there a way then, we're thinking, how to predict the graph of a function from its derivative? So I prepared this investigation or this example as an investigation or as a bridge that will connect our ideas between graphing the derivative from a function. So here we're graphing the derivative from the function. Here we're using some of the values of the derivative to sketch the function. And now we are going to move on to try and predict the shape of the function from the derivative. Now, how do we do this? So I try to jot some notes in here and set some rules so it's easier for us to follow an algorithm in order to perform this task. So when we are going from f of x to f prime of x, remember that the turning point of the function became the x-intercepts of the derivatives, or the zeros of the derivatives. I'm not saying anything new. It's a review of what we just did in the first pages of the lesson. The inflection points turned into turning points of the derivatives. Now, obviously, we have to use these relationships, but if we are going from f prime x to f of x, so remember here we were at f of x, and we went f prime x. But if we are from f prime x and we want to obtain f of x, we have to use these same relationships, but we have to read them the other way around. Okay, so we are going to say that when drawing the graph of a function from the derivative, the reverse will happen. So the turning points of the function will come from where? So the turning points of the function will come from the x-intercepts of the derivative. And the inflection point of the function will come from the turning points of the derivative. So if you are given the derivative of a function, we have to focus on the turning points and the x-intercepts of it. Obviously, and I'm guessing that you're probably thinking a little bit deeper, what happens at the inflection points of the derivative, right? So, but one thing at a time, so we're going to focus on these two elements for now, okay? So, these are the steps that I put together to graph a function when we are given the graph of the derivative. First of all, we want to identify the x-intercepts of the derivative, or the zeros of the derivative. And why do we do that? Because they will become the turning points for f of x. And then we have to identify the turning points of the derivative. The reason why we'd want to do this is because they become the inflection points of f of x. Then we have to also know and identify where are the intervals where f prime of x is positive, right? So if we know where f prime x is positive, which by the way is easy to identify by just highlighting the part of the graph that is above x-axis, so the f prime above x-axis, they will be the increasing intervals of f of x. And the intervals where f prime of x is negative, which means the values of x, where f prime of x is below the x-axis. So when we say the intervals, the interval or the intervals, right? It means that we are finding the values of x, or the mini domains, right? Where the derivative is either above or below the x-axis. So when the derivative is below the x-axis, that means that in these intervals, f of x will be decreasing. And again, remember that we are just sketching, right? And the purpose of sketching the graphs from their derivatives or derivatives from their graphs is to see the connections between them. Okay, so we're still analyzing connections rather than producing precise pieces of work, right? So here we are, we have below the graph of f prime of x. Now, it has an x-intercept at 0. And the graph is decreasing all the time. Okay, for any real number x, we have decreasing intervals. It has a turning point. So we have to think of a function that is decreasing all the time, right? So we're going to say this function is decreasing. Right. I'm sorry. I want to change something. Sorry about this. So these are graphs of f prime of x, by the way. So we have to identify the interval, the x-intercepts. There is one, there is no turning point. Now the x-intercept of the derivative will be the turning point of the graph of the function. The next thing we want to check is where is f prime x positive and where is negative. So f prime of x is positive right here. And f prime of x is negative down here. So what that means is that from negative infinity to 0, f of x will be increasing. And from 0 to infinity, f of x will be decreasing. And that's because f prime of x is negative. So we have to think of how to draw a function with a turning point at 0, okay, that has the increasing interval from negative infinity to 0. So I'm thinking if I go this way, like this is not increasing maybe, but maybe it is. So you can go this way, right? So that's an increasing line until it hits 0, and then it can be decreasing. Remember, we're unable to identify whereabout, how high or how low the turning point of the function is going to be. This is just an estimation. But what's important is that we indicate that the graph is increasing up to 0, and after 0, here x equals 0, it will decrease. Okay, we'll understand these functions, or we're going to draw these graphs with a lot more accuracy when we visit each group of functions and we find the derivatives with our special formulas that we're about to discover soon. So the next one is f prime of x. This time f prime of x is in parabolic form. So a few things we need to point at. The x-intercepts, okay? The function will have turning points. And then we have to identify where the derivative is positive and negative. So here we go. Here we have the derivative. Sorry. The derivative here is positive. The derivative here is positive. So I'm going to say that the derivative of this function is going to produce, a positive value, so the derivative will produce f of x increasing, right? Why f prime is positive or is above the x-axis, so f prime is positive, so f of x will be increasing. Okay, at these 2 points in here that we highlighted, we have turning points for the graph, and the turning point of the derivative will be an inflection point. So right here at x equals 1 would be an inflection point for the graph. So we have an inflection right here. We have a turning point or 2 turning points at these 2 x values. And down here we have the value of the derivative negative. So negative values of f prime means that the function must be decreasing here. So let's try to sketch a graph with all the information as we deduced here, okay? So what we have in here is f prime of x positive, f of x is increasing. So we can say that the f of x is increasing, making a turn here, all right? And increasing, and right here making a turn somewhere. Now you can make the turn actually at this point, right? But then we know that right here we're going to have an inflection point, okay? And then we'll have another turning point here. So it's going to be hard for us to meet the graph. So we're going to say maybe we should go ahead and increase all the way here. Okay, so right at 0, we're going to have a turning point, an inflection, okay, for the graph. And then right here, we're going to have a turning point. So the function is decreasing, and here it picks up the speed. Okay, so do you see how this happens? So we have an increasing function up to x here at this point. it starts decreasing and it makes an inflection point at x equals 1, and it keeps on decreasing up to this x value. At this x value, it starts increasing again. So this would be a predicted shape of the graph of this function, okay? So let me make this a little thicker. Oopsie. So, and here it starts picking up its speed, right? And here we go. But this would be the graph of this particular function, all right? Okay, so the inflection point could have been something like the one you see here, but the inflection point could have been possibly something like this as well, right? So how pronounced the inflection point is kind of hard to describe in this case because it will depend on the equation of the function, okay? So moving on to the last one, we have an example where we have the graph of the derivative presented by this cubic function. So most likely we're going to have some quartic function in here. Let's take a look at it. So we're going to need the x-intercepts. X-intercepts, turning points for the function. It seems that this function will have 1, 2, 3 turning points. And now we have to look at the inflection points. So I see that inflection points of the function are at the turning points of the derivative. So there will be an inflection point right here. Okay, and another inflection point right here. Okay, of f of x, obviously. Okay, so turning point of f of x, all of them. So all these turning point, inflection point, they belong, or what we mean is f of x. I'm going to erase them so there won't be a lot of writing. It's kind of confusing that way. Now, the next thing we want to look at is increasing and decreasing intervals. So here we have f of x increasing, y, f prime is positive. So we're going to say f of x is increasing. Moving on, here we have derivative below the x-axis. So we're going to say that here f of x is decreasing. And next, we have from here to here, the derivative is positive. That means that f of x is increasing. I'm going to write it inside. I'm going to use the same color so it kind of helps. And last but not least, we have the last segment in here. You can tell that the derivative is below the x-axis. And when the derivative is below the x-axis, that means that f of x must have been decreasing here. Okay? So we're going to say that the function is increasing in this interval of x values. Okay? And then it's decreasing in this interval, increasing between these 2 points, so 1 and 3. And then from 3 to infinity is decreasing. So I'm going to write all this information down. So we want to draw, we can look at it as a simple functions exercise. So we're going to say that from negative infinity to negative 1, we have an increasing function. From negative 1 to 0, we have a decreasing interval. From 0 to 1, it continues to decrease. There is going to be an inflection point in between. And then from x equals 1 to x equals 3, the function is increasing again. It will have another inflection point in between, and I'm going to separate them. It's better to separate. So from 1 to 2 will be increasing. From 2 to 1, still increasing, but with an inflection point in between. And last but not least, from 3 to infinity, this function will be decreasing. So let's try to sketch a curve with all these conditions. So from negative infinity to negative 1, we will have, from negative infinity to negative 1, we will have an increasing function. So I would go this way, right? Negative infinity to negative 1. And right here at this point, there will be a turning point. So the graph can go this way around. And then the function will start decreasing here. And right at 0, or actually a little bit to the left of 0, it will have an inflection point, which means that it will start picking up the speed, right? And it will hit a turning point right here, and it will start increasing. Okay, so it increases all the way up to x equals 3, and it will have an inflection point right at this one here, so that, and later it will turn up again, right? So here we go. I'm going to say we have an increasing function making a turning point here, and then making an inflection point here, deciding to come up at this point, making a turn right here, and then it will go all the way into the positive, so it starts increasing here, all right? And at this point right here, so it goes, it will change again, and it will still stay positive, but it will come all the way down. So let me draw the graph because this one is very slippery. So here is an increasing f of x, okay? The turning point is right here. The function is decreasing now, so we'll make it decrease. It will keep on decreasing for all the x values between here and here. And right here at this point, it will have an inflection point, so it means that we have, I'll make it a little bit. So at this x value here, we'll have a turning point. So it's still negative, right? All the way up to here. But now the speed of the function, the slope of the tangent will be positive. So the graph now will be increasing. Okay? And it will keep on increasing, increasing, increasing. All right? And it will change in here to make a turning point again. And right here, it will stop increasing and it will start decreasing. Okay. Now, again, we don't know how far up or down we go? Not yet. So what we do know is that right here the function has a turning point, and another turning point. The function is increasing, and then it is decreasing here. Let me make this a better shape. The pen is so slippery here. And then it will start picking up in speed and then decreasing again. Oopsie. And this is how we draw the graph of a function from its derivative. And it seems a little bit more complicated when we draw the graph of a function from the derivative. Totally doable. All right, so I hope that you enjoyed this lesson again, and I hope everything made sense so far. And I will see you again soon. Bye for now.